All right. Let me grab you that first thing. All right. Ready? Okay, so this should be on that first page of the notes, so you're going to go back one page next to that learning intention and do now. That nice big sheet of paper. Everybody there? All right. So first thing I want to do is talk about the basic electrolytic cell. So what are you looking for to help you identify that this is an electrolytic cell and not a galvanic cell? The first thing is that we are only dealing with one container. Yep, draw it the same way in your notes. So first thing to remember is that there's only one container. So one container, one beaker. That's what you're drawing, and also that's what you could see on the assessment is just something like this. Now, this container is filled with one of two potential things. The first thing it could be filled with is an ionic solution. Or the other thing is it being molten. Molten just means melted, if you guys remember from last year. Any idea of why it would need to be melted or dissolved?
So that the ions are disassociated?
Yes, I want my ions to be mobile. So let's draw some liquid in there. All right. Number two is I need to have an energy source. So I need to have a direct current. I have two electrodes going in. Oopsie. And my electrons will be going in this direction. You can draw it in the other direction. I'm just drawing it in this direction because that's the way I like to draw it. So you need an energy supply. Sorry, needs an energy supply. Does that mean then that these redox reactions are spontaneous or not spontaneous if I'm providing energy? It's non-spontaneous. So because redox reaction is not spontaneous. So I'm providing energy for that to occur. Cool so far? Yeah. All right. Third thing that I then need to be aware of is my anode and my cathode. This over here is my anode. My anode has a positive charge when it comes to an electrolytic cell. The reason why I'm emphasizing this is because in the galvanic cell, these charges flip around to the other order. So just be mindful. In this case, the anode is positive. The anode is where oxidation occurs. The way I like to remember that is these are both starting with a vowel. Oxidation, anode. And we can see here that there's going to be a loss of electrons. You see how my electrons are going in this direction away, following the trend of oxidation. Make sure that's. Any questions so far? Does anything need to be repeated or slowed down? You're good? All right. This then here is going to be my cathode. The cathode is negative. The way I like to remember that it's negative is that the electrons are going to it. So that's how I remember that one's negative. And this is where reduction occurs. Consonant, consonant. Reduction, cathode. In this case, it is going to gain the electrons. In this case, for the anode, we're going to lose electrons. So you see how I'm taking the redox reaction that we've been talking about previously and putting it into a real-life setting now? Yes? All right. Last sort of thing that I need to worry about then are my ions. And I'll do this in matching colors. All right, so when I have an ionic solution, either molten or dissolved, I then free my positive and negative ions so they're mobile. If I had an ionic solid in a container, it's not going to work. My negative ions are going to go towards the anode, and they're going to be oxidized. So what's going to happen at this step is that negative ions travel to the anode, where they will be oxidized. If you guys think about the elements that have that negative ion, we are thinking about the halogens. So say, for example, fluorine, chlorine, bromine, those are all good examples of negative ions. So these are my nonmetals. That's where they're going to go. What's going to happen is that these are then going to be converted back into the element. So we're going from ion to element. In this case, since I'm dealing with nonmetals, these should be forming bubbles. So say, for example, chlorine gas. I should see bubbling at my positive electrode. Poke Devontae, make sure he's awake. That green? Oh, you're right. That green's a horrible green. That better? Yeah. Ish. Yeah. I'm gonna choose an. Can you guys see this blue? Okay. Yeah. Okay. All right. Then my positive ions, my cation ions, they're gonna go to that negative electrode. Think positive and negative, opposite attracts. It bubbles because it's forming chlorine gas. So that non-metal, when it goes from that ion to the element, it's forming the gas. All right. On the flip side here, my cations, my positive ions, are traveling to the cathode. This is where they will get reduced. So you see how there's electrons over here, it's gaining those electrons to then be reduced. So I've taken my redox reaction, I'm forcing it to occur because of that electrical current that I'm providing. If we think about positive ions, we are thinking about metals. So say, for example, iron, silver, what's another good example? Silver too. Magnesium, I guess. So I'm going with my metals, and again, this is going to change my metal ions into the element. So I should get, for example, silver metal being formed. And it'll be forming on the electrode. So what I would expect to see then on my electrode is a shiny liquid or a metal coating on the electrode itself. Yep. Either you will see a shiny liquid form at your cathode, or it'll actually coat onto the electrode itself. So the outside of the electrode will have a coating of silver. That's the little electric bit. So the electrodes are, let's pull it out, this guy. Okay. Yeah. So I can stick this into the water. These electrodes can be made up of carbon, so this is just graphite, or it can be made up of a metal. It just needs to be something that conducts electricity.
So it would either be shiny or what, sorry?
It's either going to be a shiny liquid, like a melted liquid, or it's going to coat onto the electrode itself. And that's because we have a metal there. So metal coat on electrode. And we'll see that over the next couple days when I give you guys some videos. And we also do some demonstrations in class. Today, we're just doing the electrolysis of water, so we're not going to see any coating on the electrodes because there's no metal in water. How are you guys feeling about this? Okay? All right, so this is the general setup of the electrolytic cell. So whenever you see something like this on the exam, or they ask you to draw an electrolytic cell, you should be thinking, I need one beaker, I need 2 electrodes in that one beaker, I need to have an electrical source. It's a really quick identification tool.